Neural networks. The name itself sounds complex, even futuristic. It evokes images of sentient machines and artificial intelligence straight out of science fiction. But the truth is, neural networks are already shaping our world in countless ways. They are the invisible force behind everything from personalized recommendations on streaming services to advances in medical diagnosis. At their core, neural networks are simply computer systems inspired by the intricate workings of the human brain. Just as our brains learn from experience, so too can neural networks be trained on vast data sets to recognize patterns and solve complex problems. While the mathematics behind them can get quite involved, the basic principles are surprisingly intuitive. We'll explore their basic structure, how they learn, and the different types that power today's most innovative technologies. So buckle up and prepare to embark on a journey into the heart of artificial intelligence. Imagine a network of interconnected neurons, each responsible for processing information and passing it on to its neighbors. This, in essence, is the structure of a neural network. Just as our brains are composed of billions of interconnected neurons, artificial neural networks consist of layers of interconnected nodes, each performing a simple mathematical operation. A typical neural network is organized into three main layers: the input layer, the hidden layer or layers, and the output layer. The input layer acts as the entry point for the data, much like our senses provide information to our brains. Each node in the input layer represents a specific feature or attribute of the data being processed. The hidden layers are where the magic happens, extracting features and identifying patterns. Each node in a hidden layer receives input from multiple nodes in the previous layer, performs a calculation and passes the result to the next layer. Finally, the output layer provides the network's prediction or decision based on the processed information. Now that we understand the basic structure of a neural network, let's explore how information flows through it. This process is known as forward propagation. It begins with the input layer where data is fed into the network. Each connection between nodes has an associated weight, representing the strength or importance of that connection. As data flows through the network, the values are multiplied by these weights, influencing the output of each node. Within each node, a simple mathematical function called an activation function is applied to the weighted sum of inputs. This activation function introduces non-linearity, allowing the network to learn complex relationships. The output of each node then becomes the input for the nodes in the next layer, and the process repeats until the information reaches the output layer. One of the most remarkable aspects of neural networks is their ability to learn from data. This learning process involves adjusting the weights of the connections between nodes to improve the network's accuracy. The key to this learning is a process called backpropagation. Backpropagation is essentially the reverse of forward propagation. It starts with the network making a prediction based on a given input. The difference between the network's prediction and the actual target value is called the error or loss. The goal of backpropagation is to minimize this error by adjusting the weights of the connections. It does this by propagating the error signal back through the network layer by layer. Based on this information, the weights are then adjusted using an algorithm called gradient descent. This process is repeated iteratively over the training data until the network achieves a desired level of accuracy. The training regime, shaping the neural network. Training a neural network is akin to coaching an athlete. It requires patience, careful tuning, and a good understanding of the task at hand. The training process typically involves feeding the network with a large data set divided into input-output pairs. The network then learns to map the inputs to the desired outputs through repeated iterations of forward propagation and backpropagation. The training data needs to be diverse and representative of the real-world data the network will encounter in practice. Monitoring the network's performance during training is essential to prevent overfitting. Techniques like regularization and dropout are often used to mitigate overfitting. A diverse family types of neural networks. Just like there are different types of brains in the animal kingdom, there are various types of neural networks, each designed for different purposes. Let's explore some of the most common types as feed-forward neural networks, FNNs. Information flows in one direction from input to output. FNNs are used for tasks like classification and regression. Convolutional neural networks, CNNs. Inspired by the visual cortex, CNNs excel at processing images and videos. They use convolutional layers to extract features from images. Recurrent neural networks, RNNs. RNNs process sequential data where the order of information matters. RNNs are used in natural language processing, speech recognition, and time series analysis. Image recognition, a feast for the neural network's eyes. One of the most widely known applications of neural networks is in the field of image recognition. Convolutional neural networks, with their ability to extract features from images, have proven remarkably adept at this task. Imagine showing a CNN thousands of images of cats and dogs, each labeled accordingly. The network would learn to identify the distinctive features that differentiate cats from dogs, such as their ears, snouts, and tails. Once trained, the CNN could then accurately classify new, unseen images of cats and dogs. Image recognition powered by CNNs is now used in a wide range of applications, including facial recognition. Unlocking our smartphones, tagging friends in photos, and even automating passport control at airports. Natural language processing, giving language to machines. Language, the cornerstone of human communication, presents a unique challenge for machines. However, neural networks, particularly recurrent neural networks and transformers, have made significant strides in natural language processing, or NLP. RNNs and transformers can analyze text sequences, understand context, and generate human-like text. This has led to breakthroughs in various NLP tasks, including machine translation, translating text from one language to another with remarkable accuracy. Chatbots and virtual assistants power conversational agents that can understand and respond to human queries. Sentiment analysis determines the emotional tone or sentiment expressed in text, which is valuable for social media monitoring and customer feedback analysis. Beyond the obvious neural networks in unexpected places. While image recognition and natural language processing are among the most prominent applications of neural networks, their reach extends far beyond these domains. Neural networks are quietly revolutionizing industries and tackling challenges in ways we never thought possible. In healthcare, neural networks are being used to predict patient outcomes, personalize treatment plans, and accelerate drug discovery. In finance, they're detecting fraudulent transactions, optimizing investment strategies, and assessing credit risk. Even in creative fields like music and art, neural networks are pushing the boundaries of human ingenuity. The versatility of neural networks is truly remarkable, and their potential applications seem limitless. The promise of tomorrow, the future of neural networks. As we stand on the cusp of a new era of artificial intelligence, neural networks are poised to play an even more transformative role in our lives. Researchers are continually pushing the boundaries of neural network architectures, training techniques, and applications. One exciting area of research is in developing more efficient and interpretable neural networks. Current neural networks, while powerful, can be computationally expensive to train and often operate as black boxes, making it difficult to understand their decision-making process. Another promising avenue is the development of neuromorphic computing, which aims to create hardware that mimics the structure and function of the human brain. Neuromorphic chips have the potential to be significantly faster and more energy efficient than traditional processors. As neural networks continue to evolve, they hold the promise of solving some of humanity's greatest challenges, from curing diseases to mitigating climate change. Embracing the neural network revolution. Neural networks, once a niche field of research, have emerged as a transformative force, shaping the future of technology and society. From powering our smartphones to revolutionizing healthcare, their influence is pervasive and growing. By understanding the basic structure, learning process, and diverse applications of neural networks, we can begin to appreciate their power and potential. As we venture further into the age of artificial intelligence, embracing the neural network revolution will be crucial for individuals and societies alike. By fostering a deeper understanding of this groundbreaking technology, we can harness its power to create a brighter and more innovative future for all.